Hi, welcome to Angles in Circles, the next segment in deductive geometry. Obviously, what we're going to do now is move on from four-sided figures or quadrilaterals to circles, and I guess there is a burning question. Here it is in red again. Oh, red in red. What is a circle anyway? Oh, we'll have to answer that later on. I've drawn a few here and labelled certain pieces. This is screen clippings from actual Pearson's textbook for the new National Australian Curriculum. And we want to look at circles and dividing them up in various ways and having a look at any rules or theorems that might be applicable to circles. Okay, so I guess circles are pretty important, aren't they? How often are you running around in a circle? Often feels that way, doesn't it? Anyway, let's go down and start to have a look at circles. All right, here it is. What is a circle? This definition is coming from Pearson's very, very sophisticated definition. A circle is a plane curve. Uh-oh. Different sort of plane. Oh, sorry. Plane. Oh, plane, a flat surface. Ah, that's a mathematical plane. Okay, so a circle is a plane curve. It lies on a flat surface and it consists of all the points at a given distance from a fixed point. So all points on a circle, here it is over here, are the same distance from the centre. So the definition of a circle is a plane figure consisting of points all the same distance from some fixed point. And we call that the centre. We call that distance from the centre here to a point the radius. Okay, and all those radii, that's the plural of radius in the Latin, radii. Radiuses, doesn't sound too good, radii are all equal, because a circle, remember, it consists of the set of points all the same distance or equal distance from the centre. And we also, when we have drawn these lines from the centre, talk about arcs. So an arc is part of the circle between 2 points, and because that's a short one, going from A to B, it's called the minor arc. Then if you go right around the outside here, between those 2 points, the section of the circle between 2 points is called an arc. But this is the major arc, because that is a bigger one around that back side there. Okay, so there's some language. And in fact, for quite a few minutes now, I want to give you the language, the mathematical geometry language that relates to circles, things like centre, radius, arc and so on. Some of these you might know, but I'm assuming you don't know anything about it, and so we're starting at square one here. No, not square one, circle one. Oh yeah, we'll start there. All right, so come down and let's have a look at some language now. Okay, a sector. What is a sector? Well, I call it a piece of pie. Piece of pie. Like a slice out of a pie. Okay, so it's this part in here. So you could say it's the sector or part of the circle formed by two radii and an arc. But you won't be asked generally to write down definitions, but rather identify the type of sector or part of the circle and use theorems associated with it. So think of it as a piece of pie. Got that one? Hey, it might be a good idea right now to actually make some notes, make a little notebook, either electronically or in a actual book, of some of these definitions, because they really are definitions. They are the definitions of or words in our geometry language, okay, in mathematics, so that we can easily refer to pieces in circles. Okay, so let's go down to the next one. We're just learning our language here. A bit boring, but we've got to have a language, don't we? Mathematical language is special. Yeah, mathematics is special, mate. Anyway, so let's have a look at these. Let's do, what's a chord? A chord, do you play music? Yeah, well, that will help. No, I don't think it will. This one, a chord is a line joining 2 points on the circle, okay, on the circumference of the circle. So that is a chord. Any line joining 2 points. There are some special chords you've already studied in Circle Land, and that's when the 2 points you join go through, or the line joining them goes through the centre. It's called a diameter. That's a special chord. And of course, semicircles are formed, half circles. Okay, so you have a semicircle as a special what? It's a special sector, isn't it? Half a circle, semi. Okay, where have you seen that before? Semi-trailer. Half a trailer and half the motorised prime mover. Semi-conscious, only half conscious. Okay, so language in mathematics is pretty commonsensical, and generally links up nicely with your understanding of the word outside of that in English in general. So, have you learned anything yet? Possibly not, but start writing things down so you'll have a little reference book there. Okay, come down and let's have a look at another one. Okay, we're still slicing this circle up, so we have a chord, A to B, and when you join those 2 points, you have a natural segmentation, if you like, of the circle. You have a little bit cut off there between the chord and the circumference, and that's called a segment. That's a little segment, but of course over here, let's dot all this in, you have created a bigger segment of the circle by cutting this through with our chord, and the bigger segment is called the major segment. So we're getting a lot of words together just so we can talk about our circle and parts of it easily and neatly without drawing lots of diagrams. Okay, come down here. Now we're going to start talking about the relationship of angles around the circle and at the centre in relationship to the circumference. So here, let's talk about the arc. Remember, the arc is the part of the circumference joining 2 points there. So the arc AB, and it subtends, hey, what's that? Subtends the acute angle. Oh, here we are. The acute angle here is AOB, that's acute, okay, acute angle there, meaning less than 90. It is also pretty acute, oh well, for an angle anyway. So here we've got this angle here is subtended by. So I think we should define subtend. It means sits on. That angle sits on, or can be traced back to. Can be traced back to. These are Huddyisms now. Can be traced back to that arc. So if we went to that angle and looked back, where's it traced back to? A and B. So we say it's sitting on or subtended by AB. Now, the reflex angle back here, the big one around there, is really sitting on or subtended by the major arc AB. Okay, it's really sitting on that at the centre. Okay, so these are angles at the centre that we're thinking about tracing back to where they're coming from, what they're sitting on as points on the circumference. Okay, so please now start. This is a common word in circle geometry. This subtends. It means you can trace their angle back to, or it sits on a part of the circumference or an arc. So that's the idea. Arcs subtend angles. Okay. Let's go and have a look at some now. We're coming along. It's a little bit boring, I know, but we are learning a new language and getting familiar with circle stuff. So what have we got here? Let's see if we can say some things. Here's arc AB. So we would say arc AB subtends, I'd like BOA, isn't it? Is sitting on it. But we could just call it alpha. Subtends alpha angle at the centre. Is there another angle which is sitting on arc AB. Oh, yeah, look. That angle can be traced back to arc AB. So we might say, let's call this beta. We use Greek letters to stand for angles in geometry. You might Google search that or find out why that's so. Why do we use Greek letters? Is that in recognition of the Greeks' contribution to geometry? I wonder where that came from. So arc AB subtends angle beta at the circumference. So that's an angle right out at the circumference, but still traceable back to that same arc. Are you getting the idea now? All right, so let's keep going. Not far to go, and then we'll do some little proofs here. Now, angle BCA, let's do this. Angle BCA, that one, and BDA. BDA, that angle, at the circumference, standing on the minor arc AB. We would usually say arc AB subtends those two angles. They're also in the same segment, aren't they? Because arc AB, if you made a chord AB, that would be in the major segment. This is the minor piece of the segmentation when you join A and B with a chord. So this is the big segment over on the back of that. And can you see also that angles CB, what do we got? CBD, over here, CBD, that is sitting on CD. So CD, that arc, subtends these two angles, this one and this one. CAD, CAD, yeah, go to A, trace it back. I won't use that, that means parallel, doesn't it? So if we trace that back to there, what's it traced back to? Arc CD. So arc CD subtends those two angles at the circumference. All right. Not a bad one there. Starting to get used to using some of this language now. Come down. Let's have a look. More language. Angle BCA. Where's BCA? There it is. B to C to A. That's that angle. And that is subtended by arc AB here. Or it's standing on minor arc AB. What's BEA? We better rub this out because BEA is this little dude in here. BEA. That's an obtuse angle. It's at the circumference and it's standing on the major arc AB. AB is this arc right around there, the major arc. Okay. So this is sitting on that, isn't it? It's still AB, but it's around here. And so you've got a big angle sitting on that right out there at the circumference. And they're in opposite segments, aren't they? Because if you join the chord A to B, this is the big segment made by any chord. Remember, a segment is the segmentation, comes from the segmentation or cutting up of the circle by a chord. As soon as you join 2 points here, you create two segments, a minor one on the inside there and a major one. Are you getting the hang of this language? All right, let's keep going. It's going to get into some interesting stuff soon. So here's a special chord. It is the diameter. And this diameter, because it's going through the centre, it's a chord because you're joining 2 points on the circumference, but it's a special one. It's going through the centre, and we would say this angle here, angle CED, is subtended by the diameter. But we generally say differently, that is, angle CED is the angle in the semicircle. Right, joining some of these ideas together. The diameter cuts off two segments which are equal, and they're called semicircles, half circles. Okay. Okay, what's a theorem? Euclid responsible for a lot of the theorems in geometry. It's a mathematical statement which has been shown to be true. Where does it start from? Observations, where we make some observations and we make a conjecture, a proposition or a hypothesis based on our observations. And then we try to prove it. A proof is a step-by-step argument that demonstrates the truth. That is what's called a deductive argument, where we put a lot of already proven facts together and argue about the consequences of that and come to deductions or conclusions. Okay, so proof is a general thing. You don't use actual values. No actual values are used in this sort of proof here. So it's a deductive argument without any actual value. So what we're trying to do is prove that it will always be true, independent of the particular cases. Have you got it? We've started to do some of that, and this is going to be the subject of this section here. All right, here we go. Let's look at the first one. Angles at the centre and circumference. Arc AB subtends angle alpha at the centre and angle beta there at the circumference. Okay, because that angle is traced back to that bit of arc. So arc AB subtends these two. They're both sitting on them, on arc AB. What about arc CB? Yeah, let's get rid of this. Arc CB is subtending this angle at the centre and this angle at the circumference. And so we can go on. Are you getting the idea? We're going to use these and have a look at them shortly. Okay, let's have a look at the first theorem. Here's a chance to establish something. We'll just come back here. Okay, and it's still not working here. All right, theorem. The angle at the centre is twice the angle at the circumference standing on the same arc. Do we believe that? Let's have a look. If we look at that angle AOB, that's that one, is supposed to be twice that one. Well, that one's twice that one. Oh yeah, it looks pretty much like that. Can we prove it? Okay, so first of all is to draw a diagram and to state from the diagram what we're trying to prove. Angle AOB is twice ACB. The angle at the centre is twice the angle at the circumference standing on the same arc or subtended by the same arc. Let's have a look and see if we can prove it. We first of all copy down the diagram, and here we're actually extending CO to D a little bit. So let's look at some congruent triangles here. You can see that OC equals OA because they are equal radii. Triangle therefore OCA is isosceles, so let's just mark that in, that are both equal. Okay, and then OC equals OB, that one there, because that's another radius. Every line from the centre to a point on the circumference is equal on the definition of our circle, and therefore that triangle in there is also isosceles, and therefore OCB equals OBC. So let's start to mark these in. What do we get first of all? Let's put OCA, let's call that alpha, and that was alpha. And this is beta, and this is beta, because those two were isosceles. Okay, both those triangles come down, and let's have a look. And we put those reasons in, base angles of isosceles triangles there, put the reasons in brackets as we did before. And now what can we say? Angle AOD, AOD is that one in there. What's that equal to? Alpha plus alpha, because the exterior angle of a triangle equals the sum of the interior opposites. Do you remember it? If you extend the side of a triangle, then that exterior angle formed by the angle it makes with that other side is called the exterior angle. And so also in here, this will be beta plus beta, or 2 beta, because that's the exterior angle of that triangle. So let's look at how we write it down. The 2 add up to that one, and therefore AOD is 2 lots of ACO. In these proofs, it's quite handy to let the angles be alpha or beta, so it avoids all this long, big statements with letters here. Okay, and so we're going to say it again. Angle BOD, that's 2 beta now, going to be beta plus beta. So we have got that. And what can we then say? Here, angle ACB, let's have a look up here. Angle ACB is alpha plus beta. Here it is. And angle AOB, let's just go up here a little bit. AOB, that's what that one in there is 2 alpha plus 2 beta, if you like. It's twice the size. So here it's 2 lots of each of those. Therefore, it's 2 lots of that, which is 2 lots of angle ACB. I think it's a good time to start looking at introducing alpha and beta rather than referring to these big angle expressions. So we've done it. The angle at the centre is twice the angle at the circumference, subtended by the same arc. So there's our first theorem. Might write that one down. It's going to be an important tool for later on. Let's go down and look at another one. What have we got here? Well, it's the same case, isn't it? AB subtends that angle at the centre, because that's traced back, and this is a cockeyed one, if you like, at the circumference. So that would still be the same. Angle AOB under our new theorem would be twice the angle ACB. And we could prove that with that diagram as well. Okay, so it doesn't always have to look the same way. This could be bent straight over here, not bent, but swung over that way, and it would still be true, that theorem. Okay, can we prove anything else? Let's prove some more. The angle in the semicircle. Well, semicircle is formed at 2 half circles formed by the diameter, and they look like 90s to me, don't they? Any angle in a semicircle is traced back, angle at the circumference traced back to the diameter, and they look like 90s. Can we prove it? Let's have a look. Angle in the semicircle. Okay, we keep losing that. Okay, so here we are. Draw a diagram, and it's showing an angle here at the circumference, or in that semicircle, half a circle. So draw the diagram on your own piece of paper, and what can we say? Angle COD equals 2 times angle CED. Why? Well, the arc here, CD, subtends that angle at the centre and this angle at the circumference from what we just did. Angle at the centre is twice angle at the circumference. You don't have to write it in full. You may abbreviate this rule here. So like angle at centre theorem, something like that. That will do in Australian geometry proofs. Angle at the centre theorem. You fill it in, therefore. You've given enough evidence to people that you know the theorem. That points you to the theorem. You don't have to write the whole thing out. But then we can say this back angle here is 180 because it's a straight line, angle on a straight line. Therefore, CED is 90. Therefore, it's a right angle. Therefore, make the statement. So that's a nice little proof. Can you see that once we start these proofs, we can use them? We can use proofs. We can use theorems that have been previously established, like the angle at the centre theorem. Okay, we go on and put those together in our deductive arguments to prove the next ones, and so the theory builds up. Okay, angles at the circumference on the same arc. Well, let's have a look. Here's arc XY, and 2 angles are traced back to that. That's alpha, and this one is traced back. Call it beta, and you've got other arcs around here doing the same thing, but those 2 are sitting on the same arc. They look equal to me. What do you reckon? There's a conjecture. There's a hypothesis. Guess what? We're going to try and prove it. Okay, so here's the next theorem. Angles in the same segment subtended by the same arc at the circumference are equal. We don't have to put all of that. We can say angles subtended by the same arc are equal, but you must remember they've got to be on the same side of that arc. Okay, so here we are. What we're going to try and prove here is that one equals that one, because they're both sitting on or subtended by arc AB on the same side of arc AB in that same segment. And so you can abbreviate this to angles in same segment theorem. It's understood that what that means is going to be standing on the same arc. Okay, or angles subtended by same arc are equal. You don't have to put the whole thing down. Okay, let's have a look now at trying to prove that. We've found out how to write it, but let's prove it. So copy the diagram down, and what we're going to do is join O and A and B to O. And why? Because we can bring in the theorem that we had here before. AOB is twice ADB. Okay, twice that one. So if we call this one alpha, that would be 2 alpha. And also, because that's the angle at the centre theorem, is twice the angle at the circumference, subtended by the same arc, and the same thing here. Okay, because that's another angle sitting on that arc, but at the circumference. So that angle, AOB, is twice that one as well. If it's twice each of them, therefore those two must be equal. It's quite tricky, isn't it, how we are building up deductive arguments based on previously established theorems. That's very, very important. You must have a hypothesis, prove it, it becomes a theorem and then we can use that in developing more theorems and developing deductive arguments to prove other conjectures or other theorems there. Okay, let's go down, have a look at another one. Now, we've established some nice little theorems. Now let's see if we can problem solve with it. Let's find the size of angle ABC here, that angle, and giving reasons for your answer. Now this is a deductive argument. Why do you think B is such and such? So first of all, angle AOC, that's that angle, is twice angle ABC. Angle at the centre theorem. You don't have to put the whole thing in. Therefore, and AOC is 110, therefore ABC is 55. You can leave a bit of that out. We've just done it by using our previously established theorem. So you can see the value of this in identifying angles and other aspects in circles. Okay, let's do another one. Build up all of these problem-solving skills now. Now, AB is the diameter of a circle centre O. CAB, that's that angle, is 50. Find ABC. Find that one. All right. Do you recognise the theorem? Oh, this is a diameter. So this is a semicircle here. Or half circle. So guess what? We can say here, this is the angle in the semicircle. So you can go straight to it. ACB is 90. Angle in a semicircle, you don't have to put is 90. You can put angle in semicircle like that. That will do, as long as the statement guides the reader to a unique theorem. Okay. So here, and BAC is 50, therefore you can do this angle up here, angle CBA is 180 minus those two, angle sum of a triangle, so it's 40. So you get the idea. It's quite fun, isn't it? It's like a jigsaw puzzle or problem solving. You start and you bring in all the theorems you know and make up a deductive argument. That's why it's called deductive geometry. Deducing things leading to another statement and so on. Let's do another one. I've got lots for you. Oops, hang on. We've got lots for you later on. We'll just go back up here. Getting too excited here about this, mate. Okay. Okay, seeing, where were we? Oh, way back. Okay, we're up to 15. Okay. These are all points on the circumference. CAB is 48, that's that one, and DCA is 42. Find the sine of AEB, that's that one and there, and E is not the centre. So first of all, what can you say? Angle ACD is ABD. Okay, ACD is equal to angle ABD, that one. So you could call that alpha 1 equals alpha 2. So instead of that long notation, alpha 1 equals alpha 2, angle in the same segment theorem, something like that, or subtended by the same arc. Therefore, angle where are we? ABD is 42, angle EAB is 48, and therefore sum of angles of a triangle, that angle AEB must be 90. So are you having fun here? You're pinching this one and putting it over here because alpha 1 equals alpha 2, they're sitting on the same arc, aren't they? Sitting on the same arc back there. You've got to remember the theorems, so you might have to make a little note of all of those. So they're your tools in deductive geometry. Okay, so let's come down a bit and look at number 16. Just more problem solving, little puzzles. So here, this is the diameter, they say, centre is O, and F and E are points on the circumference, and here we give them parallel lines. Look at that. Okay, find a size of OFE, that's that one in there, giving reasons. Well, where can we start? Well, FOB equals ECO. FOB equals ECO. They're using the parallel lines. So you could say alpha there equals 35, alternate angle, corresponding angle, sorry. Okay, and then FOB, therefore, that one up there, I've called it alpha, is 35. Now, EOB, that one there, is twice 35, isn't it? Because it's sitting on the same arc, that's traced back to that arc. So this angle in here is 70, right? Because angle at the centre, it's getting a bit of a mess in there at the moment. And therefore, what can we say? Let's go get rid of all this and just go back here. So we've said that this is 70. Okay, and now EOF, therefore this one in here, because this one was 35, that must be 35 as well. Bit of a problem solving going on here. And triangle OEF is isosceles. Okay, OEF, I just rub this out. OEF, this is isosceles because of equal radii. Okay, so we've got this one here, and we've got those two equal radii, therefore this angle and this one are equal, and we want either of those. We want OFE, that one there. So sum of angles of the triangle, come down here, is 180, and those two base angles are equal. Okay, so take off 35 from 180 is 145, divide by 2 and share that between the two. So OFE is 72.5 degrees. Now that's a harder problem solving one. All right, let's have a look. What have we got left? Here's your chance. Okay, so here's a lot of little diagrams, and I'll pause it, and so you can have a go. Question 1 to 4, and the solutions are down below. We'll come to those in a minute. I think there's about 10 of these here. There's 5 through 8. And let's go down 9 and 10. Okay, have a go, and here are the solutions. Quite long here, lots of arguments. Check out whether you've got the arguments like that. They've got too many words in here. You can abbreviate this. You can also use alphas and betas to refer to the angles. Makes it briefer. There's question 2 and 3. Question 4 and 5. Question 6, let's see if we can get all of 7 in there. Come up to 7 then. 7. 8 and 9, and 10. Okay, want to do some more? Let's go a bit more advanced now. You understand these are all from Pearson's, of course, textbook. 11, 12, 13. 14, 15, 16. Let's look at the answers. 11 and 12 and 13. 14 and 15. 16. And some reasoning ones here, harder again. 17, 18, 19, 20. Have a look, have a go. Let's go to the answers. Oops, no, I think we've got some more here. 21, 22, 23. I think that's it then. Up 24. Nearly there. I thought there was only about 20 of those. Okay, here are some answers. 17, bit of 18. Let's go rest of 18. 19. 20, 21, 22, 23 as well there. And there's 24. Okay, and some open-ended questions here. A couple of open-ended questions. Pause that and let's have a look at the answers. Okay, how did you go? A different way of thinking, isn't it? So you've got to get into that discipline of a logical process, converging on an answer, deductive reasoning there, and I hope you're enjoying yourself with this problem solving, or puzzle solving if you like, because there is another instalment on circles coming up. So I hope to see you then. Cheers for now.